this is our textbook. I hope everyone has this textbook. If not, I also uploaded a version of this text which was sort of based on lecture notes of this Professor Steve Simon from Oxford University. It's already on CourseWeb. It's just copied from his website. And so it has a very similar text, but not exactly the same text. But this is a really wonderful textbook. I read it this summer completely from page 1 to page about here, almost completely. And I really, really enjoyed it. When I was learning this stuff, there wasn't such a textbook. But this is a really natural way to present this material. Our understanding of what are the most important things in solid state physics has evolved. So some of the textbooks written back in the 50s no longer emphasize the most important stuff. For example, the other text that I recommend, Kittel, will start by laying out all the gory details of crystal structures and things like that, which are very important, and we will cover this here as well. But this one is starting with, I can compare it to reading a thriller, a detective novel. It kind of, wheels you in. It says, okay, this is the world how we understand it from classical physics like Boltzmann theory, and this is what the solids should do within that theory, because each atom in a solid, in a crystal lattice, should vibrate in 3 directions, and we can calculate what is the heat property of that, heat capacity, and so on. And then points out a little inconsistency with that people find in measurements. When you cool down, there is a deviation from what you expect from Boltzmann theory, and dragging from that tail, like you get a little clue in a thriller, and then it unveils a whole new field of study that is you couldn't even imagine. And this is because, of course, the correct theory for describing all these things is quantum theory, and because of that, all these things that you expect from classical have a different interpretation, and then it actually does it. It starts like this here, but then it does this trick with you several times. Then it says, okay, but now we think we understand this, but actually no. If you look even closer at what people find in experiments, you find that we have to include these other things. And so there are, for most part of how this stuff was developed and how we learned about this, we learned from quantum theory and thought that we should apply these concepts for solids, and this is how a lot of this happened. But in some of the instances, solid state physics and dense matter physics was driving other fields of physics, so was ahead of other fields of physics. For example, with superconductivity, the theory that explains that then led to some discoveries in particle physics and neutron experiments and so on. So the concepts that were born from this physics were driving other physics. So we will be going through this more or less chapter by chapter, and so I put all the chapters here, and maybe there are a couple of tweaks that I've done to his curriculum, and this is based on a lecture course at Oxford University. And they have maybe a shorter semester, or maybe they're on a term system, so this takes them 7 or 8 weeks, and we will go at about the same pace. But our semester is longer, and he also does not cover some very important aspects of modern solid-state physics, most remarkably superconductivity. So we will cover that in our bit longer semester. His lectures were also recorded, and you can find online the podcast with all of his lectures. I had a great joke for this slide prepared for you guys, that if you prefer Russian accent, you can come to my lectures, but if you prefer British accent, you can watch his lectures. Except then I actually watched these lectures, and he's American. For all purposes of this audience, he has no accent. So, still, I hope I can attract you to these lectures. This is the link to his website where he has the lecture notes from 2012, which is very similar to his textbook but not complete, and I also uploaded it to our course web. All right. Okay, so what is not covered in his textbook is basically these two big topics, and this one is already classic. The discovery of superconductivity was in 1911, so we celebrated 100 years of that a few years ago, and so this is a really standard textbook material and just is not in the primary textbook for our course. For this, we could use, for example, this book by Charles Kittel, which is also written at a very good level, doesn't require too much knowledge of quantum mechanics and so on. And so we will spend a few lectures on superconductivity, as this is a profound primer in physics as a whole and also has useful applications. So we will study the experimental evidence for superconductivity, the theory behind this, and some of the electronic devices you can build out of superconductors. And then another module that I'm excited to teach, because this relates most closely to my own research, is this nanophysics of quantum solid-state physics at the nanoscale, which includes systems which are not three-dimensional, but two-dimensional, one-dimensional, zero-dimensional. So things that in the quantum mechanics class, you would solve these problems where you confine particle in a box, which is one-dimensional, two-dimensional. This would seem to you, if you've taken any quantum mechanics, as something just completely abstract, but actually we can realize these things. We can realize a particle confined in all three dimensions, in one dimension only, and in two dimensions. And so this feeds into the topic of quantum transport. So as opposed to standard solid-state physics, this is when we consider particles in a solid as wave packets, and this happens mostly at low temperatures when thermal fluctuations are subdued, and a lot of interesting effects come out of that. And one of the applications of this is quantum computing, which is something that many researchers are now trying to build. Does not exist yet, but there are many leads into this field. So this will be, basically this material will come after the midterm, and before the midterm we will focus on the main textbook. Okay, so we will assign homeworks. There will be just problems, a few problems to solve. You will have 2 weeks to solve a set, and they will be closely based on the textbook of Oxford. So by the main textbook, the Steve Simons textbook. This kind of problem-based homework will continue up to the midterm, and after the midterm I'll ask you to focus on the final project, which will be a study into one of the more modern areas of solid-state physics that you would have to write and present to the class during the last class. So this will be also the final exam will be like this. So there won't be a problem-based final exam. There will be a midterm based on what you learned to solve during homework. So midterm, I tentatively set it for November 5th, and that will be just during the regular class, solve a couple of problems, and it will be just based on the main textbook. And then the final project or final exam, this is something I hope we can discuss in detail with each one of you. That you would propose a topic and or area, and we will narrow down a topic with each one of you, that you can write something that you feel passionate about. You can use that as a final project. It's okay to solve homework in groups. I don't mind that at all. Okay. So the split of the grade will be like this. Midterm is the most important, but the others are not too far away. Okay, so this was syllabus. Do you guys have questions about this? pretty standard stuff. Yeah.
For the exams, is there a cheat sheet, or do we just come in?
I haven't decided yet, but no, I can cook up some formula sheet, or maybe I'll let you bring something. Maybe even a textbook. Not too strict on that, as long as we can check that you learn something. Okay, so here before we, so the rest of the lecture will be discussing what is solid state physics and what is the scope of the class. But before this, I want to ask you guys a little bit about your background, because I know that you come from different schools and different majors. So this class, you need a little bit of quantum mechanics, not too much. So this is, you know, the prerequisites for this course include bits and pieces of quantum mechanics. And the next lecture, so the lecture on Thursday, we will spend the entire lecture just on figuring out, you know, reviewing some of the quantum mechanics. Now, if you could just tell me if you've had any exposure to quantum mechanics, say no or yes. So some exposure, like what is a Schrodinger equation, how to find energy levels for a particle in a potential, and maybe something from chemistry like molecular orbitals and spin 1/2 particles. What is the spin of an electron? 1/2. Right. So this kind of you know, quantum mechanics will be important. It would be also helpful to know some statistical physics or thermodynamics. So be familiar with things like entropy. To read the textbook easier, maybe partition functions and things like that. But the way I'm going to teach this will not play such a huge role. I will present it to you in a way that does not really require deep knowledge of that, but to really understand it well, you know, to grasp the meaning of Fermi distribution or Bose-Einstein distribution, it would be helpful if you were also familiar with these concepts. And so, if you are struggling with these things, you know, talk to me, and we can add a little tutorial on that, or maybe I can recommend a textbook for you to catch up on these things. And this is because you know, there are many definitions of solid state physics, but the one I like is presented here. So first of all, it is what this course will be about is largely based on quantum theory. So this is you know, not a study of solids like you know, this is solid because you cannot you know, put your hand through it. You know, this is focused on why certain properties of solids come from quantum mechanics. And so quantum mechanics is at the foundation of this. We are going to build to the knowledge of solids from the quantum point of view based on very simple quantum concepts like particle in a box and so on. But this is something to really sink in and understand that most of the stuff we're going to talk about comes from quantum theory. And then what are we going to actually study? Well, solids are, most solids are crystals, and so they have atoms stuck together in regular arrangements in lattices. We will see a few examples today. But what we are going to focus on are these particles that live inside these lattices. And so the simplest particle you can imagine living inside the lattice is an electron, which hops from one atom to the other. And so it's a free electron that can travel inside the lattice. And turns out that quantum mechanics of being confined by these atoms and being able to tunnel or hop from one atom to the other defines many properties of solids, such as, is it a metal or an insulator? Does it absorb light? Is it transparent? Is it magnetic? and so on and so forth. All of that comes from electrons in periodic potentials defined by crystal lattices. But some other particles are, for example, phonons are vibrations of the lattice. And so we can think about those as being quantized, as being particles as well. And so a lot of the thermal properties of these solids come from phonons. Many other things, for example, phonons can interact with electrons. And so superconductivity is due to that, for example, due to this interaction, at least the standard superconductivity. Photons light from outside can enter solids or can be generated inside solids, and you have solid state lasers, or you have solar cells that absorb light, or you can just interrogate solids with shining light on them, and some of them reflect, some of them transmit light, and so photons can also be living inside crystal lattices. Sometimes you have electrons, and sometimes you have a missing electron. So let's say every atom contributes one electron, and one atom is different. It's an impurity. And then it does not contribute an electron. And so you can think of a fully filled lattice, fully filled with electrons, and one hole, one missing electron jumping around, and you can think of that as a particle. So, and you have holes and electrons. So studying how these particles, what energy levels they have, how they transport through the solids, how they interact with one another, is the essence of solid state physics. Now, to not be confused with the terms, I will also slip my tongue many times during the semester and call it condensed matter physics, and that's okay. To be very precise, condensed matter includes also other things. For example, some liquids are in the realm of condensed matter. Well, in principle, all liquids, but especially since this is unified by quantum descriptions, the quantum liquids like liquid helium, certainly part of condensed matter physics, but not part of solid state physics. And some other things, there's also something called soft condensed matter, which goes in the biophysics direction. Polymers and so on can also be part of condensed matter physics, not necessarily part of solid state physics. We are going to only talk about solid state physics, but you can also call it condensed matter physics. It is absolutely interchangeably. Seems from my description perhaps as a pretty narrow subject, although we all understand that solids are important, for example, because of this last point here, that they give us, the things around us are solid, otherwise we would be maybe fish in the best case, or birds. And so solids are important, but this is not quantum. Here I put these, the most famous things that came from research on the subject that we are going to see throughout this semester. Okay? So these are the things that were discovered as people like me, but maybe 50 or 100 years older than me, were studying this area. So they came up with these things, and you're probably familiar with many of them, but for example, transistor is a semiconductor device where you combine several semiconductors, at least two, and make two junctions, and then you can, by applying a voltage on the third electric, control the current that goes through. And so from that fairly simple action, but this is not possible if you just have a loom of wire, right? So this is possible with semiconductors, where you can control with a voltage whether electrons go through or not. So you build a gate, and with that you can build logic circuits which allow you to build this integrated circuit, which is now part of all the computers and iPhones and this screen and so on. Magnetic hard drive is a discovery in the field of spintronics. So when people were studying spins inside solids, so these spin 1/2 particles traveling inside solids, they found that you can actually have a different electrical current depending on whether you are going into material with all the spins lined up this way or lined up this way. And this is the foundation for the hard drive, which is the magnetic one. There is also solid state hard drive, which is built out of transistors. and it's also very similar to the CCD camera. So all our digital cameras, the camera in this webcam, is a solid-state device. Which, to build this device, the guys had to learn all the material in this course, and then they could say, "Aha, we can build this camera." But okay, this is already done, so you have to work harder. Optical devices. So these are electronic devices. These are optical devices. So interactions of light with solid can give you light-emitting diodes. So more and more light bulbs are replaced with light-emitting diodes. And by the way, coincidentally, each one of these got the Nobel Prize, except the last one. It was discovered too long ago. So each one of these is a separate Nobel Prize. Light-emitting diodes and the CCD both got Nobel Prizes. Solid-state laser, I think the first lasers were not solid-state, they were in atomic vapor, but many of the practical lasers, for example, in a laser pointer, in a CD-ROM, you guys know what that is still? Is that already ancient? So those are solid-state lasers. And so now you can get a laser for nothing, for free essentially, and stick it on a little moving head and read information that is extremely dense. Right, with a laser, okay, of course the first lasers were huge. The first transistor was very ugly, just a triangular piece of semiconductor stuck into another one with wires wired like this. It's a beautiful picture. The first LED cost $1,000 back in the 50s or 60s, and now you can buy them for a fraction of a cent. There is also a lot of engineering that follows these fundamental physics breakthroughs. But the first prototype comes from the knowledge of solid-state physics. Superconducting magnets are quite important, not only for fundamental things like bending particles to make them go around in a Large Hadron Collider and other particle accelerators, but also every MRI machine has a superconducting magnet. There is actually a volume where you have to fill in liquid helium once a month and to keep it cold, to keep it working. And without the superconductivity, this would never have worked, because MRI works with high magnetic fields of order 1 Tesla. So the field of the Earth is half a Gauss, which is half of a 10,000th of a Tesla. And to create such a field with a copper wire, it will create so much heat that the magnet would have to be huge with a lot of cooling water to absorb that heat. And with superconductivity, the great thing is current can flow without any dissipation. So forget Ohm's law, forget Joule heating, none of that. Just current just goes and there's no resistance. And so this is why superconducting magnets are so powerful and have many applications. And solar cells, obviously, the roof of my neighbor is covered with these solar cells, and I'm very jealous because his roof is just one flat piece and mine is all like this. I have this old Pittsburgh house, and it's not very handy to cover it with solar cells, but I wish I could. Okay, for those of you engineering oriented, I hope this is motivation enough to study, to be excited about studying these things. But like I already mentioned, like I already mentioned, solid-state physics is profound, right? So this is, I think, profound is borrowed from the textbook, but I really like this word. So the concepts that originate from solid-state physics change the course of the entire physics. And here are some examples. The ones I put here are the most shocking ones. There are more mundane ones or harder to explain ones that had even maybe a bigger effect than these, like the theory of superconductivity. But I can explain it with these flashy ones. For example, electrons inside a solid can sort of break up into pieces and then attach themselves to magnetic flux. Doesn't matter, we're not going to go into that too deep, but it will look like we're dealing with new particles which have a charge of 1/3. So like a quark, some quarks have charges, fractional charges like this, but this is made out of electrons. Actually, this is made out of, in principle, millions of electrons, and then due to interactions between electrons, you can divide them in a different way such that each particle has a charge of 1/3. So charges 1/3 are possible inside the solid, not outside. If you take the electron out, pluck it out, it will just have a charge of 1e and the exact mass. In solid, it can also have a different mass. It can be 100 times lighter. So it's really a bit like Alice in Wonderland. You can have magic properties inside solids. For example, electrons can attract. Two similarly charged particles can attract inside the solid. And this is also how superconductivity goes. This was a wonderful discovery. Theorists came up with this, that this is possible, and they attract by exchanging a phonon. So they sort of couple through the lattice vibrations, and they can effectively attract. So there is, of course, Coulomb repulsion. Coulomb law is always accurate, always correct, but inside the solid, other things can happen. Magnetic monopoles, right? We told you, you all took physics 1 and 2, right? And we told you that this is not possible. There are no magnetic monopoles, or at least we don't know about them. And this may still be technically true, but at least theoretically, there are some proposals that inside solids, it can look like you have a magnetic monopole. So not a real magnetic monopole, but quasi-particle created such a distribution of magnetic fields like you would have from a monopole. So all magnetic field lines just coming out of one point, which is something that's not possible outside solids. So flow without resistance or friction, I already mentioned it. Superconductivity or superfluidity, if we talk about condensed matter physics, and helium can become superfluid. So this is just liquid, and at some point it loses all friction. If you cool it down deeper and deeper, there is no more friction. So this is very counterintuitive. We try to make it useful. Unfortunately, it happens at very low frequencies, low temperatures. So we cannot, for example, transport electricity without loss. That would be fantastic. At least not yet. Maybe room temperature superconductivity can be discovered in the next decade or so. Maybe with quantum computers, we can push our thinking a bit further. But so far, the applications are not, staggeringly fantastic. But the notion that a fluid can flow without resistance is by itself staggering. You can maybe after all of this, it doesn't seem so weird, but you imagine an electron, a particle entering a solid, and then under certain conditions, the spin of that electron will travel its own way, and the charge of that electron will travel its own way. So there will be a separate spin wave and a separate charge transport happening, and this is also possible in solid spin charge separation. So of course you cannot break up spin and charge of an electron, but in a solid it can look like that is possible. And then finally, this is actually related to my topic of study. I study these objects called Majorana fermions, which are not really fermions, which are have properties which are make them neither fermions nor bosons, and they're called non-abelian anyons. This is a technical term, but again, we learn in the textbook that there are only fermions and bosons. This is all that physics gives you. You either have Fermi statistics or boson statistics. But in a solid, in low-dimensional systems, so the things we're going to learn at the end of the course, this is not necessarily the case. And so a lot of these things are just a list of more different particles living inside solids, more exotic particles. For example, these ones are Laughlin quasi-particles. These ones are Cooper pairs. These ones are Majorana fermions, and these ones are spin density waves, and so on. And so all of them are quasi-particles. So they're not real particles in a sense. Well, I should be careful what I say. They are not particles that can live outside the solid. They are fundamentally important. They are building blocks of a lot of physics, but this is emergent physics phenomena that emerge inside solids from having many, many electrons there and having them interact and so on. So this is these are not particles like electrons or quarks or Higgs bosons, but they are quasi-particles. All right, and I'm still on this idea that solid-state physics is big and important, and not like it seems from a description as something narrow. Here I show you just one morning of a famous conference, which is held by the American Physical Society in March, so it's known as March meeting, and it attracts about 10,000 people from around the world doing hardcore research. So the next one is actually in Baltimore, not too far, next March. And this is just in these 3 hours of the morning, you have 53 parallel sessions, each of them attended by, I don't know, 100 or more people. And these are just the topics that are going to be discussed in this one morning. And the meeting is a week long. You see Monday, Tuesday, Wednesday, Thursday, Friday. And you have a lot of the things I just mentioned to you listed here, and some of the other things as well. But you have new materials like graphene, you have nanostructures and magnetism, you have Majorana fermions, the thing I work on here. You have theoretical topics, experimental topics, you have magnetic molecular magnets, you have skyrmions, which are other magnetic particles, you have carbon nanotubes, electronic structure, theory, and spectra. This is something we're going to study in this class. You have 5 days of this and 6 blocks of this per day. So this is a huge, huge and very active area of current research, besides being important overall. So, okay, so in this slide I put, because I was teaching Physics 2 last year, and I realized that some of the things in Physics 2 we just give you as a given. We gloss over why this is the case. And so I know you've taken other classes since Physics 2, many of you, but just to relate to that level that we all know very well, for example, in Physics 2 we'll tell you that there are metals and there are insulators. And in metals there is conduction, so there are free electrons and they move about. And we don't tell you why that happens, why one material is an insulator, why another one is a conductor, and why another one is a semiconductor and a third one is a superconductor. So this is something that we're going to will become really clear in this course, and why some things are transparent and others not, why light goes through something, some materials like glass. We just give you, let's say, this material has this dielectric or refraction index or dielectric constant. We don't explain why this material is transparent to light and has a refraction index, and this material is just a mirror and reflects all light. So this will also be discussed here. Why magnets stick to fridge doors. So we will study magnetism. Again, we just tell you in Physics 2 that these materials are magnetic, and so they create these magnetic fields around themselves, but what is happening inside becomes left out. Why computers compute? Well, we will have a discussion about semiconductor devices and transistors and other things, and maybe even in this lecture touch a little bit on this subject as part of our motivation for the course. And this last one about energy bands and why they bend at the Brillouin zone boundaries is just because I wanted to show you that you will learn concepts that perhaps you've never heard of before. Anybody heard of Brillouin zone? One person heard. Okay, so this is not this will be very clear to you, and this is actually very important, that they bend, and it's responsible for many interesting things. You will learn about energy bands rather than energy levels, so on. Okay. All right, so now what I want to do is go through the different subjects that we're going to cover in a little bit of detail to give you the whole retrospect of the course up front, so you know where this is all going, and then we will start probably next time with quantum mechanics. So a lot of the properties of solids can be understood by simple toy models, like, for example, a gas of electrons in some box gives you a lot of useful information, but really precise properties can only be derived after you know the crystal structure. The crystal structure of solids is how and which atoms are comprising a solid, how meaning what kind of arrangement do they form. So for example, here I have three different things. Anybody knows what this is?
Salt?
Salt. This is salt. That's right. So this is just a regular salt. This consists of two atoms, sodium and chlorine. So they are arranged one after the other, and they form a cubic lattice. And so this actually is important for understanding the properties of salt. Why is salt an insulator, for example, and so on. This is graphene, right? So this is a very famous material, only discovered experimentally 10 years ago, although you could say actually the way you get graphite, like stuff in your pencil, is by stacking these layers. So the layers were already there forever, and we knew that they were just weakly connected layers. So this is a material where the connections between atoms inside the layer are strong, but we could add more layers on top, and those connections are weak. And this is why pencils, like your number 2 pencil, that's why they write so easily. You just crash off, peel off these layers. And 10 years ago, what people were able to do is to just isolate a single layer. And this was actually a huge achievement, although you could just do it with a Scotch tape. But there were even fundamental theorems which said that this is not possible, that a single layer of atoms like this cannot be stable. It will buckle or break, or they will explode from Coulomb forces. But it turns out that it is possible, and now we have graphene. Now the difference, can you tell me the difference between this crystal lattice and this crystal lattice? If I just look at one plane. Right, so this one is hexagonal, and this one is cubic. Right? So here, atoms are all on a lattice like this, and here they make hexagons. So graphene is a hexagonal lattice. Turns out that that's also very important. This is diamond, for example. There are many materials that have this crystal structure, but this particular one is diamond. So this is carbon atoms, and these are also carbon atoms. These are different forms of carbon, the same element, but very different properties, right? Charcoal or graphite, many layers of graphene is black and is not transparent. Diamond, for those of you who had the luck to see it, is transparent. So, and this is one of the hardest materials that we know. It's used to machine other things, break other things, and this one is pretty soft, at least in one direction. You can use it to write as a pencil. So the same. So chemistry is not enough to determine the properties of solids. Also, the arrangement of atoms means a lot, even for the basic mechanical properties like hardness, although this we will not study much in this course. Hardness, however, does give you different vibration properties. So this is what is illustrated here. Is a since these atoms are all connected together by chemical bonding, if you have some way of exciting a vibration in an atom, you try to wiggle one atom, or you shine some light on it, or you compress it, or there are other ways to create vibrations. Then, because atoms are all coupled together, it will create a wave, basically. So all the atoms here are coupled, and you can think of vibrations of this lattice as waves, and these are called phonons. You can talk about this completely in terms of vibrating modes of coupled pendula, for example. You can have a classical description for this, but the quantum analog would be phonons, and these phonons are, like I mentioned already, are particles. They can be thought of as particles. They are bosons. They are similar to photons, and so they obey Bose statistics, as we will see, and they live inside crystals. They give a lot of thermal properties. They can explain the heat capacity of solids. This is something that's coming up in the course next week or so. They, through interactions with electrons, they can explain why conductivity of electrons does what it does at low temperatures, and also eventually how superconductivity comes about. So crystal lattices are important for to understand the heat properties of electrons, and also of solids, and also electronic properties. So whether it's a insulator or a conductor, graphene is a conductor, whether it's transparent, or whether it absorbs light, whether it's a semiconductor, whether it has magnetic properties, all is ultimately determined by the crystal lattice. And so it is important to know what crystal structure each material has. So how do we know it, right? So we don't really see atoms with our eyes, but we can do some experiments that reveal the crystal structure. And one of the most practical techniques, of course now we have some techniques where we can probe individual atoms with scanning microscopes and so on, but to understand the crystal structure of bulk crystals, like a piece of salt, we use diffraction. Diffraction of X-ray or neutron. Why these things? Because the spacing between atoms should be comparable to the wavelength of the probing beam. Okay, so if we probe the crystal structure with just visible light, the wavelength of visible light is hundreds of nanometers, but atoms are spaced by angstroms, and therefore there will be thousands of atoms that would fit in one wavelength. We will not be sensitive to the response of individual atoms. So we need waves that are short, like X-ray, or neutrons are also waves, but all particles are waves, right? We know that. All particles are waves, and so neutrons are heavy particles, so they have short wavelengths, suitable for probing crystals as well, suitable for probing the angstrom size dimensions of crystals. And so the way it goes is you have a source of these particles, for example, an X-ray tube. So this is just a material where you apply voltage and it emits X-rays. And then you have some X-ray optics, like a hole in lead, which collimates this beam and makes it go, all the X-rays go in the same direction. And then you put them through the crystal, and behind that you have a screen, and you see a diffraction pattern there. And the physics here is the physics of diffraction gratings. So if you have a diffraction grating and you shine a wave on that grating for certain angles of outgoing light, you will have diffraction maxima, and for the others you have diffraction minima, and from the spacing between these maxima, right, you can determine the spacing of the grating. Now in this case, the grating is the crystal. So atoms themselves are the diffraction grating, and it's a three-dimensional object, so there is a lot of geometry that you have to figure out. You shine light from different angles and you get very different patterns. So for example, this is an example for salt for one specific pattern. So from the positions of these points and these dashes, you can figure out what is the arrangement of atoms in this crystal, in this salt. That there, you can figure out that there are two different atoms, and that this is a cubic lattice from the symmetry of these points. And we will study in some detail how you can interpret these kind of pictures and how you can tell the crystal structure from diffraction experiments. This technique is also, by the way, it's very important in polymers. So in biological studies, for example, the structure of DNA was discovered this way. But to apply this technique, you need a crystal. And so what people do is they take biological molecules, very complicated molecules, and they crystallize them. So they make a lot of them, synthesize a periodic structure out of them, often at low temperatures. And then by analyzing the details of these patterns, which can be much more complicated, they can figure out the arrangement of atoms in very, very complex structures, not just in this very simple cubic lattice, but in much more complicated things, which can also be solids, for example. Complex oxides are much more complicated than the salt and other things. Okay, so we will see how we can study this crystal structure, and then we will also spend a lot of time on thinking about what electrons do in these crystal lattices. This is a very basic picture of what happens. You have periodic arrangements of atomic nuclei. These atomic nuclei are very small objects, but from the point of view of an electron, they are attractive potentials because nuclei are positively charged. They have neutrons and protons inside. The radius of the nucleus is very tiny. It's a thousandth of an angstrom, very small. And these shapes here are Coulomb potentials. So this is 1 over R. And so electrons that live around these nuclei would be trapped in these potentials, and those would be atoms. So from a quantum mechanical point of view, we can say that these electrons form energy levels inside these potential wells. The electrons fill up energy levels inside these potential wells. However, if we look at just one of these wells, then the situation is clear. There will be a possibility to fill electrons into some of these wells. The electrons go typically 2 per level, or if there are level degeneracies more. We will discuss that on Thursday in more detail. But as we bring these wells closer and closer together, there could also be levels that sort of sit above the potentials. Potentials will drop a bit, and there will be electrons that are not confined to one potential, and so they're allowed to travel everywhere. So then a lot of the physics of solids comes from the fact of whether electrons form this level that is delocalized, not confined to one well, whether this happens or not. So if it happens, you have a metal, or maybe if it barely happens, if it almost happens, you have a semiconductor. If you have an insulator, that means all electrons that you have that came with the atoms, all of them are sitting on these lower levels, and they are too deep down and cannot jump and escape and travel from one to the other. So if you have electrons that are free and are living here, Then one picture you can imagine of a solid, which would be a metal, would be this classical picture or semi-classical picture of little balls, which are electrons bouncing in between the fixed nuclei, which are the scattering centers for electrons. And this is a very powerful but rather naive theory, which is called the Drude theory, which I hope we'll get to next week, which is very helpful in many situations, but is also very wrong on many levels. Okay. Yeah?
So this is probably a dumb question, but so you said like you have a semiconductor if it's just barely touching the tops and stuff. So would a material be more conductive if there are more bands above it, or does that not make it?
So the answer is it depends on whether electrons fill the entire band or if there is some room left in the band. So if there is room left, then they're conducting, and if the entire band is filled, they're not. But to give you a more clear explanation, we'll have to study quite some stuff. Okay. Yeah. So this is still very naive, what I'm showing you here, just to give you a flavor with not going too far from particles in a potential. And so I'm already telling you that even this picture that, okay, they delocalize and then they become these balls that scatter everywhere is rather naive because it does not include Fermi statistics of electrons. So this is something we're going to also study. This is another level of complexity that you can imagine already, is that in this model, nuclei are all fixed. They're like rods in between which balls bounce. But you could imagine that electron interacts with these crystal sites and pushes them. So they're all positively charged, the electron is negatively charged, so there might be a little force of attraction between the two. And so this is called, well, there are many manifestations of this, but if the electron is flying through at some speed and interacts with these particles, he will create a wave. Yeah? Like a boat on a lake going through will create a wave. And so this is how you can have electron-phonon interaction. Or you can think about this object as a new particle, which is called a polariton. So it sort of pulls together charges, and then nuclei become a little bit, this region becomes a slightly different charge, and it attracts more electrons there. And so actually what travels here is not one electron and then a wave, but actually a cloud of electrons. So there are more and more complicated effects that you could study by thinking about electrons as charged particles in this lattice. And quantum mechanics adds even more ideas to this. Okay, magnetism. We all know this picture, I believe. So this is iron filings that line themselves up around the big piece of iron. And so we know from this picture that we have north and south poles. We don't have monopoles at this level. And that all the magnets have their own magnetic dipole moments, which make them align like this. These are all macroscopic phenomena that you can easily see. You can just stick a magnet to your fridge door, although I was really shocked that in my house the fridge door is non-magnetic. And all the magnets, I had to fit them on the side of the fridge. And I don't know who would do such a cruel thing. I think I have to complain to the manufacturer. Now, what's behind this is, well, one of two things, right? So what has spins inside solids? electrons have spins, and a lot of it is explained by electrons, but in principle, also nuclei have spins, right? Protons and neutrons have spins, although those happen to be about 1,000 times weaker coupled because of the gyromagnetic ratio that includes the nuclear mass. So proton mass, so that is in the denominator, and so the effect of those, the magnetic moment of those is much weaker. So the same spin, 1/2, but magnetic moment is much weaker. Now, how would you, so each spin, we know what spin does. It's a magnetic moment, which is intrinsic to a particle. Well, it's a moment, and then it gives a magnetic moment through gyromagnetic ratio. But we can think of spin as magnetic moment for the purposes of this course. And so each one of these spins would create a field like this around itself, right? So it will have its own virtual north and south pole, and it will send magnetic field lines going all around. And so one way you can imagine creating a large effect outside the solid with really field lines that you can see in a picture like this is if all the spins were lined up in the same direction, and their effect would magnify, right? So they will all add up and create these huge magnetic field lines that you could see outside. Because if you imagine electrons as magnetic moments that point randomly and fly around inside the solid, you will have no effect outside, right? And that's a non-magnetic material. And in a magnetic material, there should be some kind of order. So there's this idea of macroscopic ordering. So through interactions or through the particular crystal structure of solids, through the masses of atoms, and even the temperature can play a role. For all these parameters, some solids decide to line up all their electronic spins in the same direction. So there is a macroscopic order that emerges. From the statistical physics point of view, there is a very deep area of phase transitions that deals with it. So you have a phase transition from disordered, all the magnets pointing in random directions, to ordered state, which could be a ferromagnetic phase transition. And ferromagnetism, this is a cartoon for it. This is how it looks. Now, this particular ferromagnetism is actually, turns out this is not by far the most common thing that happens. This also happens, but what happens more often is something like this. This is a cartoon I took from the internet, but the idea is the following. You have more spins pointing up than spins pointing down. You have both, but you have more of one kind. And the way it happens is that they live in sort of different potential wells, where for one spin species, for example in this cartoon for the spin down, the bottom of the potential is higher, and so they all fill up to a certain level. This is because they're fermions. We will review that in the next lecture, but you can think of them as water in a tank. They fill to a certain level regardless of where the bottom of the tank is. That's why there's a sea level, even though the bottom of the sea has different heights. And this sea, this is Fermi sea, just equilibrates at this level, but it turns out you have then more spin up than spin down. And then there is net magnetism that creates this magnetic field around the material. So the reason why the bottoms of the two wells have different depth is profoundly quantum mechanical, and this is towards the end of the textbook is going to be explained there. Okay. Okay, so superconductivity is really one of my favorite topics, and that's why I already mentioned it to you 5 times. Let's look at the picture on the right. This is an experimental graph from 1913, I believe. 1911 was when helium was liquefied, and then to reach these low temperatures, these are Kelvin, so you have 4 Kelvin, 4.2 Kelvin, 4.4 Kelvin, you need to be able to dunk a specimen into liquid helium. So before 1911, this was not possible to reach these low temperatures. So this is 4 degrees from absolute zero, so this would be 269 Celsius with a minus, and God knows how many Fahrenheit. I'm still very bad with Fahrenheit. So what happens here is this is, there's a little R here, so this is resistance, and this is temperature. And what these people in the Netherlands were measuring in 1913 is resistance of stuff at low temperature. So they managed to liquefy helium, so they got a new tool, and what could they do with it? They could, look at things at low temperatures. So they looked at resistance. And what they found was that resistance goes down with temperature. And this is something that we maybe will touch upon in this course even, and in most materials, resistance goes down with temperature. If you have a resistor made of metal, which is 1 kilo ohm at room temperature, it can become something like 300 ohms at low temperature, easily. It can drop. So at least for metals, it's the case. Some things actually increase in resistance. So anything is possible. You can have a slight increase in resistance. It can go insulating. What this did, and this was mercury, it dropped to 0. And he puts 10 to the minus 5 ohms. This is as good as he could measure. So 10 micro ohms was his resolution at the time, and it is these points down here that correspond to this resistance. So as he could only reach to about here with his liquid helium, and he just was able to observe this effect, and this was not a fluke. This happened every time, and this happens, as we know now, with many materials. And this is also a phase transition of another kind. There is a global order involved. It's a transition that you can see by resistance. So resistance vanishes. But superconductivity, even though it derives its name from this observation back in 1913, is more than just vanishing resistance. So all the properties of superconductors cannot be explained by just saying that this is a perfect conductor. You can build an electrical circuit with a perfect conductor, that would explain a lot. But for example, wouldn't explain this. This is a teapot made of a superconductor. It's a high temperature superconductor, so it works at much higher temperatures. This is 4 Kelvin, and this works above 77 Kelvin. And why this is great is because 77 Kelvin is the temperature of liquid nitrogen. And this is very easy to create, very cheap. Still, you have to handle it. It evaporates pretty fast, but this is just air which can be liquefied fairly easily. So you fill this teapot with liquid nitrogen, and you place it above something. Who can guess what it is?
Magnet?
It's a magnet, right? So you place it above magnet, and it levitates. So it is not only a perfect conductor, it turns out that it's also a perfect diamagnet. So it creates the field exactly opposite to the field that is outside. And so by creating that field, it creates like a screening, like a repelling force, which allows it to levitate. So people, you can build trains, for example, that would travel without friction. They're called magnetic levitation trains. Doesn't actually have to be superconducting. You can just put 2 magnets like this, but also you can do it with a superconductor. And so superconductivity, what I wanted to say with this picture is there is more than just resistance. So this is comes from Meissner effect. This is a nice illustration of a Meissner effect. All right, and now finally these are semiconductors. So this is how I can explain semiconductors to you in an easy way. Silicon is one of the most famous and most important semiconductors because we hear about silicon technology, silicon industry, because all the chips that power our IT technology are silicon based, although people try to build other ones. In silicon, you have several electrons around each silicon nucleus. And the way silicon is arranged, all of these are engaged with other atoms. So actually there are no free electrons. So it should be an insulator, except if there are some impurities, like this phosphorus atom that made its way into a silicon lattice. Phosphorus comes with one extra electron. So in this emptiness of silicon, you add one extra electron on top, and then that electron can hop from one atom to another and makes it weakly conducting. And now why is it a semiconductor is because of this. So it's not really conducting, but partially conducting, and especially because now we can tune it from being conducting to being non-conducting. And not just by removing this phosphorus, but for example, by building a capacitor incorporating the silicon. So if we make another electrode here and apply a potential to it, we can make this electron disappear, go somewhere outside of the material. And then because there are so few of them, we can remove all of them. And so we make this piece of material from conductor to insulator. And this is the foundation of transistor and of all the CMOS technology that we have in our computers and cell phones and so on. Okay. So the last 5 minutes or so, I'm going to talk about that, the technology. I know a few of you are engineers. I don't know if you're electrical engineers or
engineering physics.
Engineering physics.
Yeah.
Okay.
We do some electricals.
Anyhow, this is important enough. If you haven't seen this before, I think this is great. Have you heard of Moore's law? Moore's law is famous, right? So Moore postulated that the size of the number of transistors per unit area doubles every so many years, right? And this has been going on for quite a while. This graph I have here is already a little bit old, to 2010, but I think it's still going. That means that these silicon transistors that work on the principle from the previous slide get smaller and smaller, and so also things like physical dimensions, and the number of atoms that participate in each transistor, reaches some ceiling. We cannot go much smaller than that. But this has been great for us from the early processors to Pentiums and beyond. We've been just scaling down these silicon chips. This is how one looks. Again, this is from 2010. So this has 383 million transistors, and the size of this chip is about this big. So each transistor looks like this. There is something called a channel. Channel is a piece of silicon where you can have electrons or nothing. Then there is this gate, which is a metallic structure that you apply voltage to, and it by electrostatics controls how many charges you have in the channel. And so you can completely deplete it. That means you close the transistor, or you can open it by applying a positive voltage. You attract charges into the channel. By applying a negative voltage, you make it negative. You have source and drain, so current flows. And so this is how we build our logic, solid state memory, and all the things. And this one structure is now 32 nanometers inside. So this is just about a few hundred atoms long, maybe not even 1,000 atoms long, maybe 1,000. Yeah. So this is getting very small. This is why I want to dedicate part of the course to nano science and technology, because this becomes important in our daily lives. what are the issues that become important? First of all, just the reproducibility from transistor to transistor. This is a diagram of a transistor with the channel, which is silicon, and these dots are these donors, these phosphorus donors that contribute electrons to the channel. So each one contributes one electron. And here is the gate, which is the active part of the transistor, where we can close or open the transistor by applying a voltage here. And so you can see that there are just a few donors left there. This is actually can fluctuate from one transistor to the other. In one of them you can have 30, in another one 35, in another one 32. So there is just statistical barrier that you hit by making it smaller, besides all the quantum properties of these donors that can also become important. So technology is doing amazing advances, but other problems come about. And this is the ultimate transistor. These are two examples where people in research labs, not in industry, but people have used just a single atom to make a transistor channel. So in this structure here from Australia, there is this one atom of phosphorus, which is an impurity, and there are two contacts, and electrons from here can hop onto here and hop off, and you can control with another gate here whether they can do that easily or hard. And so you cannot make a smaller transistor than this. And there is something very similar that was done actually at Pitt in Levy Lab with different materials, not silicon and not phosphorus, much more complex materials, but also very small structures of a few atoms. So this one is really one atom, single atom transistor. So this is possible in the lab. And of course here we really have to think about this process as quantum mechanical tunneling onto a box where electrons are confined. So here is fully quantum mechanical description that we have to use to think about these transistors. Okay, and so we hit this barrier of physical dimensions, and so Moore's law is bound to fail. We cannot make smaller transistors for much longer, and that's why the engineering community is thinking about many other ideas, either going sideways, like building architectures that couple different chips, so expanding the footprint, or maybe going three-dimensional, and sort of advancing the silicon technology, which is called CMOS, which is called complementary metal oxide semiconductor logic. So sort of making engineering improvements to that, or doing different materials like carbon, strongly correlated materials where interactions between particles give you extra functionality on spintronics, using spin instead of charge as an information carrier, and building devices with other capabilities. So transistor is just controlling the current with a gate, but you could, for example, incorporate memory into this gate. You can have not a binary, but 3 different settings, and pack more functions into the same volume. And in these directions, solid-state physics going forward plays a crucial role, providing new materials, new architectures, understanding the quantum aspects of new devices. And so that the end of our course we will see some examples of more modern technologies like spintronics, quantum computing, that fit into this extended roadmap for CMOS. This one is actually proposed by an international society, which is called ITRS, and this has also been updated since, but this is to say that solid-state physics, 50 years ago we had one transistor which was discovered in a lab, in Bell Labs, and 50 years later we have 300 million transistors. Maybe solid-state research that is done now on a single prototype device will drive the technology of the future in the ways that we can predict. And this is why we need to keep studying solid-state physics. We need to keep learning about these things. All right, so we can stop here.
Any questions? Not, then I'll see you on Thursday. We'll review quantum mechanics.